Hello, this is the second part of Chapter 1, which we deal with straight lines and linear functions. So today I'm going to be looking over 1-3 linear functions and mathematical models, as well as 1-4, which deals with the intersection of straight lines. So getting into the first part of this. This is something they posted in the book because we're going to be looking at some more real world type problems here. Although the circumstances they're giving you are very much simplified, it would not be as simplified in the quote unquote real world. But essentially, the whole idea of doing these real world problems, application problems, a lot of you know them as word problems, is that students will say, well, this doesn't apply to me, and you try to show how it does, and then they say, well, that's a word problem. I don't like word problems. Well, that's how that's what most of the applications are going to be. They're going to be circumstances where you have to formulate the solution. You're not going to be say, okay, here's what we need an answer to, and here's how you're going to do it. It doesn't always work that way. So. But getting into more two other important definitions, a function is a rule that assigns to each value of x one and only one value of y. So, so basically, we're going to see other versions of how that could be seen, but essentially, if I plug in a number into a function, I get back only one other number. It's not gonna. If I plug in 2 to the function, I get 3, and the next time I plug it in, I get 7. It doesn't work that way. A linear function generally has the form of f of x equals mx plus b, where y is being replaced by f of x. Really not much different. I mean, when we do a graph of lines, y is being treated as a function of x to begin with. So for our first example, determine whether the equation defines y as a linear function of x. If so, write it in the form y equals mx plus b. So let me give you a moment to think about that and answer these following questions. Okay, so it's kind of the way they ask this question is kind of misleading because determine whether the equation defines y as a linear function of x. If so, right? Basically, you're going to attempt to do this because by attempting to do that, that's what's going to tell you if it's a linear function with respect to y. So, for instance, if I look at the first one, if I subtract 2x from both sides, I get minus 4y plus 9 equals negative 2x. I subtract 9 from both sides, I get negative 4y equals negative 2x minus 9. Then if I divide both sides by negative 4, I get y equals negative 2 over negative 4x plus a negative 9 over negative 4, essentially. And so y is going to equal 1/2 x plus 9/4. So it's written in the format. I mean, I can clearly say that this is m and this is b. So yes, this is a linear function. For b, it looks very similar. I'm still going to go through the same process. I'm going to subtract 2x squared from both sides. Negative 8y plus 4 equals 2x squared. I'm going to subtract 4 from both sides. That should be a negative 2x squared. And I'm going to divide both sides by 4. I can divide both sides by negative 8. Again, I had to distribute, so negative 2 divided by negative 8 is a positive 1/4 x squared. Negative 4 divided by negative 8 is a positive 1/2. Looks very similar, but this is squared. If that x is squared, this is actually what we would classify as being quadratic. And we're going to see quadratic functions as we proceed through this course as well. We're not going to be able to avoid them. So this is not a linear function. It's a function, but it's not a linear function. It's a quadratic function. And last but not least, C. Again, I see where the y is. I'm going to subtract 2x and 8 from both sides. Just kind of cut to the chase. I'm going to divide both sides by -3. Now this looks almost linear, but except this is squared. And if I go one step further to get rid of that, to get rid of a square, I have to apply a square root. So if I square root the left-hand side, I just get y. On the right-hand side, since I'm treating y as the variable, I'm going to do a square root, and I also have to put a plus or minus symbol there. Now, there's all sorts of things wrong with this. First of all, it's not in the format of a linear function. It's not in that y equals mx plus b format. So it certainly is not linear, a linear function. As a matter of fact, here I have a single x value producing two different y values, one when it's positive, one when it's negative. So for instance, if I put 0 in there, I would have the positive square root of 8/3 and the negative square root of 8/3. Those are two separate answers for y produced from one value x. This thing's not even a function. Let alone linear. So when they ask you, oftentimes they give you an equation, you need to figure out if it's a function, where y is being defined as a function of x. Solve for y, or solve for whatever variable they're asking you is supposed to be a function of something else. That's how you go about doing it. This was kind of a misleading question because it says, oh, make the decision first and then write it in that format. Well, no, it's by trying to write it in that format that lets you see whether or not it can be written as a linear function. If it can be, it is. If it can't be, it isn't. So that's pretty straightforward there. Moving along. Linear functions and mathematical models. Cost, revenue, and profit functions. So they're just defining what they are here. We're going to be making use of them. Cost is the total cost of manufacturing X units of product, so how much it costs to make this many, whatever it is you're selling. The revenue is how much money you take in from selling it. Obviously, you want to sell it for more than it costs you to make it, so you can make a profit. And the profit function is just basically the result of me subtracting those two, taking my revenue, subtracting away my costs, and what I left over is my profit. Now, it's a very real-world type situation, but the circumstances you're going to be given are not going to be totally real-world circumstances, because when you look at cost, revenue, and profit functions, and we're also going to talk about supply and demand curves eventually, they don't tend to be linear. They tend to be much more complicated graphs than that, but if you can't understand how to do the linear graphs, you're going to have a considerable more difficulty dealing with the other types of graphs and how you would, come up with formulas and things like that. So, some more background. Costs incurred in operating a business are usually classified in two categories. You have your fixed costs, which are basically, to put it in a real world circumstance, like your costs for like basically opening the door that day. You have to use so much energy. You have to have a space to have it in. Those costs are going to be there. Then there's costs for, you have to bring materials in to build whatever it is you're building or make whatever it is you're making. Those are variable, because if you make less, then you don't need as much of that, so you're spending less on that. So those are variable costs, and that's usually based off of like cost of materials and things like that. So suppose a firm has a fixed cost of F dollars, a production cost of C dollars per unit, and a selling price of S dollars per unit. And the cost function. They make this sound much more difficult than it is. I'm not going to get into that too much. But essentially, again, the things you're looking for is that you're going to often have your cost function having, a cost per unit times the number of units plus some fixed cost. You have to try to see what that is, and sometimes they'll just come out and say, hey, you have fixed costs. Usually the revenue function is just going to be it's going to be a linear function, but there's not going to be a y-intercept, so to speak. And the important thing again here is that if you want to find profit, you take revenue minus cost, essentially. So try that information out for this problem here. It's breaking it down for you. It's having you do it in pieces here. So a manufacturer has a monthly fixed cost of $100,000 and a production cost of $14 for each unit produced. The product sells for $20 per unit. What is the cost function? What is the revenue function? What is the profit function? And how many units would the manufacturer need to produce in order to possibly break even? Now, since they're giving you monthly fixed costs, you should be basing all this on monthly values. So this is all in a month span. But there's the question. Take a moment or two to answer it, and then we'll go over it. Okay, so they give us the two costs, a fixed cost and a production cost per unit. And we're going to let X equal the number of units produced and eventually sold. As we work with these, we're kind of making the assumption that everything we produce is being sold. And that is another simplification that you're dealing with here, because we know that that's not necessarily the case in the real world circumstance. So the cost function, C of X, I'm going to have $14 spent for each one of these, whatever it is I'm making, in a month. Plus, I'm going to have $100,000 to basically open the doors of my business each month. So those are my fixed monthly costs. My revenue is going to be, well, I'm selling them for $20 a unit, so it's going to be 20 times X. So my profit function is R of X minus C of X, which is 20X minus 14X plus 100,000, which would be 6X minus 100,000. So that is my profit function. In part D, you're asked, how many units would the manufacturer need to produce in order to possibly break even? Breaking even, I mean, there's different ways of defining it. I mean, basically means that you've at least covered the cost. You've sold enough units to cover the cost of making those units. So basically, breaking even means I'm not making any profit. The profit is zero, but I'm not making a loss either. So you can either say, well, I want to see when these two are equal. But when those two are equal, that means that if these two are equal, that means that this is going to be 0. So basically, I want to see what value of X for the profit function, which is this, 100,000, will make that equal to 0. So I'm going to solve that. So I'm going to add 100,000 to both sides. And I'm going to divide both sides by 6. So I have 100,000 divided by 6. And when I do that, I get 16,666 and 2/3 or 0.6 repeating. So basically the break even, if I round this down, I'd still be making a slight loss. So I would say I should be selling 16,667 units need to be sold. Because I can't sell 2/3 of a unit because I don't know what this is, and 2/3 of something could just mean it's a broken something. So whatever it is. So, example 3. An office building worth $1 million when completed in 2003 is being depreciated linearly over 50 years. What will be the book value of the building in 2017 and 2018? Assume that the scrap value is $0. So we didn't give a whole lot of background on this, but basically, if you think about it, okay, we're starting off with an initial value. The building is worth $1 million. So we could say, okay, X equaling the number of years after 2003, and worth of the building is my Y. So in 2003, which means there's no years past 2003, I'm at 1 million. Yeah, there you go. It says it's depreciating linearly over 50 years, which basically means at year 50, we expect this building to be worth nothing. So we want to figure out what would the depreciation be. What's the rate going on here? So basically we have two ordered pairs. We have 0, 1 million, and we have 50, 0. I want to get a rate of change. A rate of change is just another name for a slope. So I want to get a slope for this. So the slope is going to be 1 million minus 0 over 0 minus 50. So I'm going to have 1 million over negative 50. And 1 million over negative 50 is a negative 220,000. So basically the building loses $20,000 in value per year. And we have an equation that would predict what's going on here, since I know that this is a y-intercept, because the x value is 0. So I know that, I have the slope, I have the y-intercept. So the equation of my line, y equals negative 20,000 x plus 1 million. So now it's asking me for the value of the building in 2 different years. So essentially, the way I defined it is that, okay, well, in 2017, that means that x would have to be 14. So, and this is actually going to take the place f of x, if you want to. So I'm going to figure out what f of 14 is for 2017. So negative 20,000 times 14 plus 1 million. F of 14 equals $720,000. 2018, no doubt, means the x is going to be 15. So f of 15 is going to be negative 20,000 times 15 plus 1 million. So f of 15 equals about $700,000. So there you go. Kind of a roundabout way of asking you a question and giving you some coordinates, but that's how they will sometimes do that in real life scenarios. You'll have these data that will help you define your line, and it's all right there. You just have to know how to make use of it. But as I said, a lot of these kind of graphs usually are not extremely linear either. So not entirely an overly realistic circumstance, but still, headed in the right direction as far as the real worldness goes. Another instance of using linear functions for our purposes is to look at linear demand and supply curves. Much like the curves or the circumstances we were talking about in the previous exercise or example, typically supply and demand curves are not linear. We're just kind of considering them that way for the time being because that's where we are in this course and your level of understanding. But they're based off of a couple of principles here. So you have linear demand, which in a free market economy, a consumer demand for a particular commodity depends on the commodity's unit price. A demand equation expresses the relationship between the unit price and the quantity demanded. So what they're saying here is, okay, we're defining the unit price, P, to be some function of X, where X is the number of units of whatever, okay? So this is X, and that's P, and the vertical axis is price. The demand curve, if you think about it, well, if you have something really, really, really expensive, you're not going to have a very high demand because people aren't going to be able to afford it, only a few people. As you bring that price down, the demand increases. So that's why you would tend to see a demand curve look like this. If it's linear, it's going to have a negative slope. So the demand curve is going to have a negative slope. Because again, as the number of units get bigger, as the price goes down. Okay. On the other hand, when you look at a supply curve, in the competitive market, the relationship between the unit price of a commodity and its availability in the market. So basically, to kind of say some of what they're saying here, if you're the manufacturer, the producer, whatever it is, if you're not going to make a whole lot of money off of it, and you can't sell it for very much, you're probably not going to put a whole lot out there. The more money that you can get, the more you're more willing to put more out there. It's like, it's like, well, I don't really have, you need to sell this for 5 cents. Well, that I can't sell it for 5 cents. So if you want me to sell it for 5 cents, I'm going to make 2. But it's like, okay, well, you'll pay $100,000 for this. Okay, I'll make as many as you need. So generally, the supply curve, which if it's linear, will kind of go up in this direction. It's going to have a positive slope. Because again, as the price increases, the more units they're willing to put out into the marketplace. This is what we call equilibrium. This is studied a lot more in business calculus too, where you actually have curves other than lines. But an equilibrium is generally the best price to set, this whatever it is, because that's going to be a situation where you have the supply and demand being equal to each other. So, you're not going to have surpluses. You're not going to have declined quantities and shortages and things like that. You're going to be producing the amount that people demand. So now, granted, in the business world, they don't usually try to do that. I mean, they purposely sometimes try to make shortages because they could drive the price up because people need to have that new toy for Christmas, whatever it is. So an example. Read over this. Well, let's take a look at this. The quantity demanded for a certain brand of cordless headphones is 200 units when the unit price is set at $90. The quantity demanded is 1,200 units when the unit price is $60. How many of the cordless headphones would be demanded if the price per headphone were $45? And at what price would the cordless headphones have no demand? So consider those two questions. There's more to it. You have to figure out a few more things to answer those questions, but let me give you a few moments for you to try, and we'll come back. Okay, so you had time to answer these questions. So let's see how your answers compare to what I'm about to show you. For me to answer these questions, I need to have a supply and demand curves here. I need to know what's going on. I need to know what equilibrium is and so forth and so on. So the first thing is what I have here is I'm given a couple ordered pairs. When X is 200, the price was at $90. And when X is 1,200, the price was at $60. So these are ordered pairs that I'm going to make use of here. Now the thing is, as we go through this, I'm going to figure out what this, this is. This slope is 90 minus 60 over 1,200 minus 200. Oh, sorry, I reversed that. I did the cardinal no. I started with the 90, which means I had to start with the 200. So that slope is going to be 30 over negative 100, which reduces to, double checking my math here. No, it's 1,000, yeah. Which equals a negative 0.03. So we have the demand curve here, because that's what's going on here. We have a demand curve. We're not going to be able to come up with a supply curve because we don't have any information about how much is going to be put into the marketplace. So the demand curve, d of x, looks like it's going to be equal to negative 0.03x plus some initial amount, which basically kind of corresponds to how many would be demanded if this thing were free. I mean, there's some things out there that, if you don't want it, even if it's free, why would you even want to have it? So we got to figure out what this guy is here. So to figure out what that value of b is, I'm going to need to put in that ordered pair, which I put a little square around up there. So my demand price, remember, because this is number of units, this is my demand price. Okay, so it's still the price is what we're actually doing here. So at $90 for price is when my X value was equal to 200. So 90 equals -6 plus B, which means B equals 96. So basically that means that, that I have my price based off of the demand curve being defined as -0.03x plus 96. So essentially, what we're doing here, if x were to be 0, which means nobody would want it, and this is what we're going to get to the next question. Nobody would want it. X is 0. Then that price would be $96. Okay, because it says what unit price would the course be have no demand. So essentially here, no demand means that no units are wanted. And that means that the demand curve price was set at $96 or possibly more. So, see, I was a little off when I said it before that, when we're looking for B, we're looking for, how much it would be worth if there was, how many people would want it if there's nobody, if it was free. It's the other way around, actually. So, so there's your answer to that question. So if the price were set at $96 for this particular cordless headphones, based off of, if assuming it's a linear model, I wouldn't have any demand for it. So certainly, any kind of equilibrium would probably be much lower than that. I just don't know what it is because I don't know what the supply is as well. So, the next part is dealing with the intersection of straight lines. Now, this is something that's been done in a lot of Algebra 1 classes, so a lot of you may have seen this kind of work before. But let me kind of demonstrate how to do it in various ways. Now, we will eventually learn in the next unit dealing with matrices, and we'll also learn the elimination process. The two methods we're gonna look at in this particular unit or chapter is dealing with using a calculator to help you with it, or secondly, to use a process known as substitution to help you find the solution to these kind of questions. So the first part I'm going to do is a quick demonstration of how you can use the calculator to find the intersection of 2 points. Now the whole thing about it is if you want to use technology, just about any calculator out there, the linear equations need to be in the y equals mx plus b format, slope-intercept, because it's also a function format. If it's not in this format, you have to change it to that format. Or at the very least solve for y. Even if you don't solve completely for y, as long as y is alone, if you took like point slope and kept the parentheses in there and just added or subtracted the number that was next to the y to get y alone, that would be sufficient as well. So, but essentially, I'm just going to do a quick demonstration. This is my pseudo calculator here. Let me turn it on. It's a simulated calculator. If I want to find, for instance, I have these two lines here, 3x plus 2 and 2x plus 3, and I'm going to graph them. Okay, so basically, I got them in here. I'm just going to clear that. Clear. Come on, clear. No. Clear. Clear. That's good. So you just type in the equation that you have in slope-intercept form. And now with those two equations entered, all I do is hit graph. Now, depending on who used it last or what have you, it may not be seen quite as well as this. And yours may not be in color or things like that. So that's all, and I'm just going to see if I could, so you can see the results of it here. That's all fine and good as long as you could tell which line's which, based off of other things. Now, if it's not showing up this nice, go to your window and define your axes. I mean, the x min and x max say how far left and right you're going on your. So I'm going from -10 to 10 on my x-axis. The scaling I'm showing is going by 1, so each dot represents a unit of 1. And you see the same thing for the y min, y max, and y scale. The rest of the stuff don't touch if you have it there. But now I can see where the two lines intersect each other. So if I go to my calculator, go to the calc menu, you can see choice 5 is intersect, so I'm just going to hit 5. And it's going to say, ask for the first curve. Since they're lines, it doesn't matter which curve is first, which one's second, and you certainly don't have to take a guess because if they're going to cross, they're only going to cross in one place. And there's the intersection point. So I could say, based off of this, that the intersection point is at 1, 5. Or the solution to that system of equations. So if I look at example 1, as you see there, it says you want to use your calculator, but the main issue is it's not in a format for me to use the calculator yet. So I'm going to have to put it into that format. So for the first one, I would subtract 2x from both sides. And then divide by 4. So I'm going to have -2 divided by 4, which is a -1/2 x plus 11/4. For the second equation, I'm going to add 5x to both sides. So I have 5x plus 5. And if I divide by 3, I'm going to have y equals 5/3 x plus 5/3. So now when I go back to my calculator, move that aside a little bit. I'm now going to put these in, clear these. I have -1/2 x plus 11/4. I have the second y one being 5/3 x plus 5/3. And I'm going to graph them. So there's my first line. There's my second line. And I'll show it here too. And I can see where they cross each other. And it looks like they're crossing each other at a point that's, not quite at 1 and not quite up as high as 3. So, you're going to maybe get some nasty decimals. Now, what the problem is, if you were doing this yourself, you'd have to guess where this is. If you were trying to just say, okay, I'm just going to guess by looking at the graph. Now, luckily, I could just go to the graph and say, okay, second, calculate, find the intersection, and just basically hit the enter 3 times. And I can see that the intersection is at 1/2 and 2.5, or 1/2, 5/2. So I can see that. It's just, if you have a point that's kind of floating out there and it's not on a nice gridded area of the graph, you would have to sometimes speculate as to what that is. A lot of people would usually guess at the halves, but here it happens to be that, so it actually did work out. But graphing is really only a useful tool if you have a graphing calculator to do it. because you want to get the exact answers. And even sometimes when you use the graphing calculator or things like that, it doesn't produce the exact answer because it uses certain algorithms to kind of check a lot of answers, and sometimes it may be off by a decimal point or two. Um, so there's other means of doing it, and one of the other means is to use some algebra. Now, here we want to use substitution to find the intersection of the lines given by the following equations. So substitution is typically used if I have at least one equation solved for a variable, and here I do. If it isn't, if you don't have that, you can always solve one of the equations for that variable, and you could just use it like that. That's fine. But oftentimes when you're doing that, as you've seen, when you often are solving an equation for y, you end up with fractions, and you have to kind of be aware of your fraction rules. And sometimes that freaks some students out. So I'm going to use this to, basically replace y in this function here. So I know y is the same thing as 2/3 x minus 4. So I come to that second equation. I'm going to say, okay, x plus 3 times 2/3 x minus 4 plus 3 equals 0. So I'm essentially replacing y with what it equals, and what it's doing is I now have an equation that only has x in it. So I can figure out what x is based off of this. If I distribute that 3, I'm going to have x plus 2x minus 12 plus 3 equaling 0. If I simplify and combine like terms, x plus 2x is 3x. Negative 12 plus 3 is a negative 9. I would add 9 to both sides and divide both sides by 3 to get that x equals 3. I'm not done yet. Remember, I'm looking for an intersection, so I do need an ordered pair. A lot of students get into this habit, especially ones that struggle in math, and I got an answer, it seems to make sense, yay! And, I got x equaling a number. Well, you're not looking just for x, you're looking for y too. And now what I can do is go to take this y equation again and now replace the x with 3. So y equals 2/3 times 3 minus 4, which is y equals 2 minus 4, y would equal a negative 2. So the intersection is at 3, negative 2. Let's make sure everything's cool here. Good. I'm looking at some notes as I'm doing this, and some of the notes, I must have been thinking something else and they were wrong. So, next example. Break-even analysis. A division of Carter Enterprises produces personal income tax diaries. Each diary sells for $8. The monthly fixed costs incurred by the division are $25,000, and the variable cost of producing each diary is $3. Find the break-even point for this division, and what should the level of sales be in order for the division to realize a 15% profit over the cost of making diaries. So take a moment or two, seeing how what we've done previously can help you figure this out, and then I will go over it with you. Okay, so first off, we're asking for a break-even point. So, and we do have enough information to come up with a cost function and a revenue function, which means I can figure out a profit function. Okay, and we know that the break-even point is when the profit function equals 0. No profit, and if I have a negative profit, that would mean a loss, so I don't have that either. So the costs. It says we have a fixed cost of $25,000 and a variable cost of producing each diary of $3. So it's $3 for each diary, which I'm going to let X be number of diaries. Plus $25,000. The revenue, well, they sell for $8 a piece, so it's going to be 8x. So P of x is going to be the Rx minus the Cx again, which is 8x minus 3x plus 25,000, which equals 5x minus 25,000. So that's my profit function. Now with that profit function, as I said, I want to set it equal to 0, so I can figure out how many diaries have to be sold essentially for me to break even, or this company to break even. So I'm going to add 25,000 to both sides. Divide both sides by 5,000. So to break even, the company needs to sell 5,000 diaries. For the second part, what should the level of sales be in order for the division to realize a 15% profit over the cost of making the diaries? So we're looking for an X value here. I want my profit to be equal to the cost function, or the cost, plus 15% of the cost. So I want it to be 15% higher than that. So that's what I'm looking for. So I want to see where my profit, 5x minus 25,000, would equal 1.15 times 3x plus 25,000. So I'm just going to simplify and solve this for x. 5x minus 25,000 doesn't change much over here. It's pretty much simplified. 1.15 times 3 is 3.45. 1.15 times 25,000 is 28750. I'm going to subtract 3.45 from both sides. 3.45x, I should say. I get 1.55x minus 25,000 equaling 28,750. Just to make more room here, I'm going to add 25,000 to both sides. 28,750 plus 25,000 is 53,750. And then I'm going to divide both sides by 1.55. And I get x is equal to 34,677.42. So to realize this profit, the company needs to sell 34,670. There's always debate on this. I mean, if you just round it off and say 77, you're okay. I would say 78 though, because it's saying that to make that level, you have to get 34,677 and a little bit more. So I'd rather be over that level than under. So that's just kind of reasoning I'm using. So if you want to say 34,677, that's fine too, because you're just rounding off, and that's sometimes that they'll accept as an answer too. So this statement here is just kind of repeating some of the things I've already mentioned. talking about the market equilibrium. And the equilibrium is basically the price that you would like to set. It's the intersection of where the supply and demand curves actually do meet up. And with this information here, and what we've gone over so far, I want you to take a moment, read through this. The other thing you need to be aware of is that they're using, see here, it's like the demand function. If I could get the pen to show up again. They're saying the demand equation, instead of saying that P is D of X in this case, they're just saying that's P, and the same thing here. That P is S of X. Essentially, they want you to find, essentially where these two are at equilibrium. When, they want you to figure out the X value and, of course, the price as well. So find the equilibrium quantity and the equilibrium price, because that's what it's going to be. The X is going to be the equilibrium quantity. The P is going to be the equilibrium price for the fax machines. So take a moment, work this out, and see if you can come up with the answer. Okay, so look over this question. It's the last question for this video. Try not to be sad. There's many more videos you'll get to see. I make myself laugh sometime. Anyway, so we're looking to find a system of equations, or solve a system of equations, where we have 3x plus p minus 1500 equaling 0, and 2x minus 3p plus 1200 equaling 0. I want to see what x and p values work out for that. So now for the time being, I am going to continue to use substitution. This is a circumstance I would normally use elimination on, but we haven't reviewed that yet. If you happen to remember elimination at this point and know how to do it, by all means, you can certainly use it. I'm not going to hold that against you. So since it's easy to, when I look at these equations, that this one here, I can isolate p pretty easily just by adding 1500 and subtracting 3x from both sides. I'm going to use that. I'm going to solve that one for p. So p is going to be 1500 minus 3x. Since I'm not graphing it, I don't need to have it in a particular format. I can have the 3x come second. It doesn't matter. I'm going to use that as a substitution into the second equation. Never substitute into the same equation you just manipulated. Okay, if I put 1500 minus 3x in for p right now, what I would end up getting is 0 equaling 0, which basically is just say, oh, 0 equals 0. It means something else in other circumstances, but for this one, it wouldn't mean, it's meaningless. I am going to come down here and replace the p with 1500 minus 3x, leaving everything else alone. But now my equation only has x terms in it, doesn't have a p term anymore. So what I'll do is I'll distribute the negative 3, so I have a negative 4500 plus a 9x plus 1200 here. If I simplify, I have 11x minus 3300 equaling 0. 11x, adding 3300 to both sides, and x would be 300. So that is the equilibrium quantity. Now I got to find the equilibrium price. So I'm now going to come back up to here and do another substitution. 1500 minus 3 times 300 equals 1500 minus 900, which is 600. So the equilibrium price is $600 per fax machine. And that's all there is to it. Not to say make it sound it's overly easy, but if you have any further questions, please make sure to bring them up in class. I'll be more than happy to answer you. Until next time, I'll see you around. Bye, everybody.